In this session, we will be looking into some standard machine learning metrics and paradigms. So the area of ML the area of ML has exponentially grown in the past few years, essentially driven by the availability of a lot of data. That's because of, again, the presence of biomedical devices that are ubiquitous to the extent we could have a biomedical device even at home right now with us. So if that's the case, users are generating data on an exponential basis. So that has led to the learning framework, in which case the digital systems are programmed to understand patterns, or in other words, they're trained to memorize the patterns which goes beyond the human capacity or the human intelligence. So ML is a subset of the bigger area of artificial intelligence. So if we were to take the artificial intelligence area as a big circle, this is AI, then ML becomes a subset of this AI. That's a green one. So it's part of the AI. This is ML, or machine learning. Then within this machine learning is another subset, the red one, called the deep learning. Okay. So I would like you to get an understanding here. I mean, it's deep learning is a very specific aspect of machine learning. Machine learning goes beyond neural networks, which is a building block of deep learning. Machine learning looks into other forms of pattern classification, like LDA, linear discriminant analysis, logistic regression, support vector machines, decision trees, and so forth. So the many techniques available out there. And depending on the application and the context, each one will have their own optimal performance. Then artificial intelligence is a broader area which goes beyond machine learning. It brings in other aspects such as in robotics, human-computer interaction, and wherever we wanted to substitute the human aspects of it, automation, and also in augmentation. Okay, so you got to keep this in mind, and specifically what you would be seeing in this course are ML techniques or machine learning techniques here. Now, going one step further, it's getting obvious that we need to have a good collection of data. We need to have a good collection of data. And the data in this particular course are typically the signals that are coming out of the biomedical sensors, okay, because this is about biomedical signal processing. So the signals constitute the data here, but that could be expanded by including other information such as the demographic factors and clinical factors. So for example, if I'm collecting my ECG, extracting features from ECG are definitely input to the machine learning model. In addition, I can also input other demographic factors such as age, gender, geographical location, behavioral habits. So this way, you are enriching the data set that's been sent into the ML model. When we do all these things, we got to keep a couple of things in mind. In designing an artificial intelligence system, or a machine learning system driven by data, we got to ensure that the data has been ethically approved to be used. So ethics clearance is very important. Okay. For example, in Ryerson, if you were to do any experiments in collecting data, we have to go through the Research Ethics Board approval, okay, what's called REB. So ethics clearance is an important aspect of it. Otherwise, we cannot do the experiment or even report the outcomes of the experiment. Okay, that's the number one aspect of it. The second thing is how do we protect the privacy of the participants? Okay, so privacy is another thing. So both ethics and privacy has to be a part of the design process. It cannot be an afterthought. It cannot be an afterthought. Okay. When we talk about privacy, we are talking about are we revealing any identifiers? Are we revealing who this person is that? Okay. So for example, if I collect my ECG, as I said, if I'm collecting ECG features like heart rate variability parameters, collecting age, gender, and so forth, as long as it's anonymized, like it doesn't identify who that person is, then you're protecting the privacy to some extent. Okay. So this is very important to keep in mind, especially as I indicated, now we could even do data collection from home, and we have to guarantee this to the users that the privacy is of a paramount importance. We have to be mindful of these things because at the end of the day, this allows us to scale up our data sets. So the database or data sets is the key component of ML. Okay. ML, as indicated before, similar to what we have seen before, here the input to the machine learning model, are the features, the feature vectors, and the output is the decision function D. Unlike what we have seen in the filtering process where the input was X and the output was Y, the X and Y were of a long sequence. But in feature extraction, as you know, the size of the features, let's call it 1 by M. And if your original signal had the size 1 by N, by going through a feature extraction process, we came to F. Okay, so this is a feature extraction process. There are many ways to extract features. Is there a science behind feature extraction? Not really, so it tends to be more experimental, like how many features are needed is experimental. But one thing we know is that M is far less than N. Okay, so that's a dimension reduction problem because of the curse of dimensionality that's involved in sending X directly to machine learning. We reduce the dimension as much as possible so that the computers can design the decision boundaries or the classification metrics, because now it can handle the data and it can overcome the curse of dimensionality. So the feature extraction, we are starting to see that it could be in time domain, it could be in frequency domain, or it could be in both time and frequency domain. All those things are important. Okay, and in certain signals, we know what kind of features play an important role. We know about certain features in ECG, like rhythm, heart rate variability features. In speech, we also have an idea that fundamental frequency and the formants play a significant role. So we extract those features from those signals, X. Okay. So this F, when fed to the machine learning, the decision is that whether you wanted to classify in simple applications, we just classify the signal to be a normal signal or an abnormal signal. In some cases, we go beyond two-group classification, like multi-group classification, for example, in emotion. So nevertheless, that the size of the D is very, very small. It's just either a two-group or an, for example, few groups, not more than that. Okay, so that's the thing. So it's basically from N we go to M, and in the decision function we again have classes C. Okay, and the C would be far less than N and M for sure. Okay, so I can call this as C. In this case, the C vector is of size 1 by 2, two groups. So if you see here, the C is less than M for sure, and M is far less than N. Okay, so overall what has happened is that right from your sensor, to the time we make an inference or a decision of a given signal, it goes through a lot of dimension reduction process. I could see this in a very different way. We could even see this as some form of a quantization process. Okay, if you remember, one way to reduce the continuous function in the y-axis is through the process of quantization by taking finite levels. Exactly, that's happening. Okay, so here we are doing kind of a massive quantization in going from the signal to the features to the decision. Okay, so the decision, as I said, is dependent on the machine learning framework. Some do a very good job in making the decision. Some obviously needs to be optimized. Okay, so this machine learning model is really gets its strength from the available data sets and how diversified is that data set. Okay, that's the third thing to keep in mind. In your data sets, you got to have the aspect of equity, diversity, and inclusion in your data collection process. Okay, so as much as possible, you have to have a diversified profile of people that you're enrolling in the study, and you would be as inclusive and equity in your approach. So that EDI, equity, diversity, inclusion, should be a consideration in your data set preparation as well. Unfortunately, in many data sets that are available out there, some of the elements have been missed, and they tend to focus on a narrow group of population. So what happens is that your AI model, the machine learning model, tends to be biased. Okay, so the bias is not created by the algorithm. Bias is created by the human curator who's preparing this data set and making the machines understand it. Okay, so if we do a good job in making sure that we have included as much of diversity in our data collection, then obviously the machine learning will be able to understand that. Okay, so the problem is not the technique. The problem is what we feed into the algorithms. Okay, so that's why it's super important in data sets to keep that in mind. Okay, so more the signals, the better. And in a lot of biomedical application these days, we are starting to get good information from diversified people, so that the ML decision, which is based on, as I said, training the digital system essentially to understand it. So it's similar to what we have seen before in filtering. We were designing filters to do some kind of a processing on the signal. Here we are similar to that. We are designing in the system to essentially learn from the data that's been fed, which is X, but we cannot feed the X directly. So we feed in the form of F. Okay. So it's important to keep that in mind, and the role of data sets will become clear. So let's assume that we have gone through the process of ethics clearance and made sure the privacy aspects are taken care, and the data set is as diversified as possible. This diversification is also important from your own point of view. Rather than me collecting my own ECG just in a specific time in a given day, like if I'm just collecting, let's say around 4 to 5 p.m., it's very narrow. A good thing is to diversify the data collection. I should collect one in early morning, in afternoon, late afternoon, and one in the evening. So for example, that gives a variation, a dynamical profile of that. Then the machine learning tends to understand the what's called the intra-subject variability. Okay, keep this in mind, intra-subject variability. We will talk about inter-subject variability for sure, but also there is a lot of intra-subject variability, and that's what makes this whole field very interesting. Okay, now how would we assess the performance of a machine learning outcome? We have come across a high-level introduction of the various ML techniques available out there. And they could fit into the domain of supervised learning, unsupervised learning. In supervised learning, as you can appreciate, the data sets that are available to you is labeled. Somebody labels the data set beforehand, saying these signals are normal, these signals are abnormal, and we feed those labeled information to the ML system to train it. And then we test the system with an additional data set to see how robust they are. Okay, so this is supervised learning. In an unsupervised learning, we don't have the label information, so nobody tells us the signal is normal, abnormal. We just see how they get clustered in a feature space, and we make inference out of it. So unsupervised learning essentially doesn't depend a lot on the domain experts, whereas in supervised learning, because somebody has to label your data set, we need to rely on the domain experts. So if you were to do a project, for example, in understanding what's happening to the EEG signals during epilepsy, for example, somebody has to label that this particular ECG signal had gone through epilepsy, and that labeling information should be available for the ML technique to understand. Okay, so now how do we assess the performance of ML? There are quite a few standard ways to approach, and I would like you to keep this in mind because this becomes super important in your project. To essentially, in the final part of the project, you will be indicating the success of your project in the form of these performance metrics. Three simple concepts to keep in mind. One, what's called classification accuracy. The second one is sensitivity and specificity. And the third one is an ROC curve, or in other words, rock curve or receiver operating characteristics curve. Okay. So how does it work? How does these performance metrics work? Okay. One matrix that you need to understand is called the confusion matrix. The name is kind of misleading. It says it's confusion matrix, but it's a pretty clear matrix to understand. Now, what happens in this confusion matrix is that depending on the data sets that are available with you, you would be assessing the performance of the data set in the way that whether your machine learning, for example, if it was normal, if the signals were normal, that's a ground truth. And if your signal was abnormal, again, ground truth. By ground truth, we mean somebody has labeled, and that label is given by the domain expert. That's the ground truth. Okay. Now you would see the predicted thing and would see how much of this normal were predicted as normal, and we call that as, for example, a small a. Okay, small a. Now that small a is called as a true negative. Okay, true negative. So somebody doesn't have the disease, and the ML has predicted, yes, a of those cases who do not have the disease are in fact a negative. Okay, so that's true negative. That's A. Now, in some cases, the person would have been negative, but the ML would have predicted that to be abnormal, and that B variable is called the false positive, FP. False positive is not good in many medical applications because in this aspect, the person might be put under undue stress of going through health intervention, therapy, and so forth, and they may not have the disease. So the false positive is quite important to keep in mind, or in other words, good to minimize it. Now, the third one is that somebody is abnormal, but the system says they're normal. Okay, so that's the C variable here, and we call that as false negative. Okay, so somebody is basically having the disease, but the ML is predicting that person does not have the disease, and it's false negative. You can appreciate false negative in the current context, especially if somebody is having COVID, and the ML techniques, let's assume we have an ML technique to detect COVID, and your COVID detection scheme is telling the disease is not there. Then you are basically having the person undiagnosed, and they could be a spreader. Okay, so the false negative is totally unacceptable in this current pandemic context. That the person is having the disease, but the system, the testing system, either it's an ML testing system or it could be just using your biological samples, is telling that person doesn't have the disease, is dangerous because now that person feels they don't have the disease and they could be a spreader. Okay, so false negative is also not desirable in medical applications. Okay, now comes the important aspect is a D. So somebody is having the disease and your ML has been trained to predict that person does have the disease. Okay, and that's the variable D, and we call that as true positive. Okay, so this is how the confusion matrix is formulated. Okay, And how would you predict it? You can use any of the ML techniques that you will come across. Okay, in your project, you would have decided that you would use something like a support vector machine. Yes, that's the mechanism to arrive at those predicted values. Or you might decide that you would use a simple decision tree by all means, or a base classifier. So the ML choice is up to you. And you could see there's a plethora of techniques available. Even the approach of convolution neural networks and deep learning fits into that ML approach. Okay, so that's algorithmic power. So some algorithms do a good job, some ML techniques do a good job in getting the right elements for us. Okay, so if you look into this, essentially, if your ML is doing a good job, and also you have done a fairly decent job in the feature extraction part, and going back even further, you've done an excellent job in filtering out your signal from various noises. Then you might be end up in a very good confusion matrix. When I say a good confusion matrix, is something that has a good diagonal values. Okay, so if these values are dominant, strong, A and D, essentially you're getting the true negative and the true positive, A and D. If these values are high in the main diagonal, and you're essentially trying to make the B and C zero, okay, that means it's a fantastic classifier that you are designed. Okay, so you got to strive to make sure this is a very high value. If okay, and obviously the C and D are zero, or if not, they take a low value. Okay, so that's a good design of the machine learning technique. Now, can we put a number to that? Yes. So that's called the classification accuracy of your system, and the classification accuracy of your system. The classification accuracy of your system is given by this formula here, okay? And it's nothing but, you can see true negative plus true plus, so A plus D divided by A plus B plus C plus D, okay? So that's the classification accuracy. Higher this number, better the performance. Okay, so this is what you hear out there, that you will hear, okay, certain systems like speech recognition system is giving you a performance of 80%. That means it's 80% classification accuracy. Okay, that is, ML is doing an 80% good job in giving the results that we want. Okay, in terms of the true negatives and the true positives. Okay, so typically uh, having a higher classification accuracy is great, but you got to keep in mind, especially in the medical domain, the classification accuracy is just a tool for the decision maker. Okay, so if you're involved, for example, a neurosurgeon is trying to use ML technique to guide the performance, like in neurosurgery, and they've done some machine learning on the data that's available for the neurosurgery. And if the classification accuracy is coming out to be 80% in that particular application, then it's up to the neurosurgeon to use that outcome in the decision-making process. So that's why ML is seen as a tool in computer-aided diagnosis. Okay, so you got to remember, this is just a toolkit in the computer-aided diagnosis. Okay, computer-aided diagnosis. Some people call it as CAD, computer-aided diagnosis, or CAD area. Okay, and this is obviously even more important when people are looking into data that are medical images. Okay, medical images is very common. Like people go through various X-rays, CT scans, MRI scans, and ultrasound scans, for example. Now you could use ML to find out, are there patterns that are concerning, are there any abnormal patterns, and that would flag to the radiologist. So the radiologist, rather than spending the time into looking into these images on a high volume basis, which could lead to fatigue, could use the computer to aid the decision making in coming to the point, okay, there are certain features that are present in the images that might need some attention. Okay, so computer-aided diagnosis role is quite crucial in radiology and in medical image-based diagnosis as well. Okay, so the classification accuracy is something you have to keep in mind. Now, the other certain small modifications we can do is people use the word sensitivity and specificity in the classification, in the ML classification metrics. Now, sensitivity is that how good is your technique in picking up abnormality or the disease presence. Okay, so it's simple. It's nothing but true positive divided by a false negative plus true positive. Okay, so this expression is with the given matrix example would be D divided by C plus D. Okay, C plus D. So, for example, if your C is low or zero, then your sensitivity is very high. It means your ML is really sensitive in diagnosing the diseases. Okay. Again, in the COVID context, you will realize that sensitivity of the certain testing schemes uh, is not very high. I mean, I think the accuracy rate varies. It's not definitely 100%. So what happens is that it depends on various factors, whether the swab was taken in the right way, whether the sample had the viral particles present. So sensitivity is something that people are striving to make it higher. So the disease diagnosis is pretty robust. Okay. Ideally, we would like to have whatever device or AI system we are developing to provide 100% sensitivity in picking up the disease. Okay, that's kind of the ultimate goal for most of us. Now, specificity is also important, and specificity, as you could understand, is basically uh, telling whether the disease is absent. Okay, how good is your ML technique in picking up normal cases and ensuring the disease is absent. Now, again, looking into the metrics here, it's true negative by false positive plus true negative. So if you look into this, the expression of true negative variable is A, and false positive is B. So it's nothing but B plus A. Okay. So again, if B in this particular expression is 0, which means there is no false positive, the specificity is very high. Okay. So in designing ML techniques, we all look for having a very high classification accuracy, very high sensitivity, and very high specificity. Okay. So if you have all those three variables which are high, it means your ML technique is good. The moment you get one of them very low, for example, you do have high sensitivity, but if the specificity is very low, that's not good, because that means your ML technique is kind of doing a bad job and it's giving more false positives. Okay, and vice versa. So we strive to make sure that all these variables are giving high values. And this is exactly you would be also reporting in your project, what was the overall classification accuracy and sensitivity and specificity of the particular problem that you're dealing with. Okay, so here you could see that it involves everything, right, from signal noise removal in the beginning pre-processing step to feature extraction. Those features get fed into the ML technique, and the ML technique is one of the many techniques that you could select. And the outcome of an ML technique, independent of the technique, we use this confusion matrix. And from the confusion matrix, you can get these ABCDs. And from the ABCDs, you can easily give the different metrics: classification, accuracy, sensitivity, and specificity. Okay. So this particular slide is important. And normally you could also do this both at the training phase as well as testing phase. Okay, let me explain what that means in the next page here. Now, let's assume you have 100 samples of signals with you. Okay, 100, for example, let's assume 100 EMG signals with you. Now, you don't use the entire 100 signals to train the machine learning system, because that's not the good way. Normally, what is done is that you split that 100 signals into 60, 20, 20. Okay, so the very first thing I'm pointing out here is that we would use 60 signals to train the machine learning model, which means it's learning from the data. Okay, now you would use the 20 signals, or 20% of that, to validate. This is just to fine tune your ML decision boundary which is automatically done to ensure that your metrics that you're looking at, like classification accuracy, specificity, are pretty high. That's used for validation. Once that's done, then you would be testing out the whole thing by exposing your ML technique to an unseen data before. Okay, so now you can imagine, okay, the model has been trained, it's available to be deployed in the real world. Now I'm testing out. So in that case, you would use 20% to test out. Okay, if the testing also the accuracy rate is high, that means you've done a great job. Okay, sometimes what happens, you get very high accuracy in the training and validation stage. You get very low accuracy in the testing stage. When I say accuracy, it's a classification accuracy. A model which is giving very high accuracy in the training and validation stage and very low accuracy in the testing stage is set to overfit it. Okay, the model has overfitted. Okay, on the other hand, if you got a low accuracy in the training and validation stage and a higher accuracy in the testing stage, then that model is said to have underfitted. Okay, so it's a balance between overfitting and underfitting. How do we achieve that balance? We have to experiment it and see it. It's not easy to tell at the outset that you've designed a great model. It's always the trade-off between underfitting and overfitting in a machine learning thing, and it all depends. Sometimes you might get the overfitting, for example, because of lack of adequate data signals. So here in this particular example, 100 signals may not be appropriate because the model has overfitted. So you need to look beyond 100 signals. So that's why in ML applications, people are always hungry for data. More the signals, more the variation of those signals, the better the model would have been done in terms of minimizing overfitting and underfitting. Okay, so such models are obviously called have very good generalization. So you got to develop a ML model which has a good generalization, which means there is very little of overfitting and very little of underfitting. They're called models which are generalizable. In some applications or in some books, you see it in ML, like you could even take 80% of your sample size to train the system, and you would use the remaining 20% for testing it. Okay, because the only difference here is that with the previous approach, your training model was tweaked to ensure that we are doing a robust job by validation process. But if you don't have time, because validation does take time, if you have to deploy something very fast, like a rapid response, then you may not have time for validation. So you would use the entire 80% of the data for training. Okay, so this is just a suggestion. Now 80-20 split or 60-20-20 split is a good practice. But a lot of other groups, a lot of ML workers, what they try to do is that they even go with a 50-50 split. They use 50% for training and 50% for testing. You could take any split that you like to have, but it's been shown repeatedly that an 80-20, 60-20-20 provides meaningful and results which are robust. When I say robustness means, let's assume that we are developing an ML model, for example, for the city of Toronto. And if I want to scale up this globally, if I want to make the same system apply globally, and you got to ensure that the system is robust. Again, here you may not have the luxury of collecting the entire world's population data. So whatever ML you're designed with Toronto's population should be scalable. And you could really do some kind of a testing in the robustness from this validation and whatever has been discussed. So here, a good ML engineer is somebody who could really design a good ML model with a small data set, and that same model holds on if I expand the data set to a very big data set. Okay, that's where a good ML designer comes into play. Okay, so here obviously you invoke various concepts that we have seen so far. You make sure you have done good pre-processing, feature extraction, and you have selected the appropriate ML technique. Now, as I indicated, overfitting is the common problem in a lot of the biomedical applications these days, and we don't recognize it. And I can even guarantee that in the 24 projects we have, most of them will have the overfitting problem, and that's something unavoidable because of various factors, and we will also touch upon that as we go along. Now, the other way, if you do have a lot of time in hand to basically develop a very robust system, the approach that people use is called a cross validation. Okay, cross validation, just like how you have seen before, if you have 100 signals with you, you would use 80% of that for training, let's say, and 20% for testing. But what I would do is that I would be making sure that 80 and 20 signals are independent of each other. In other words, it's a very bad approach to use the same signals that were used for training to test it. That will introduce bias, and your ML results are not going to be correct. Okay, so you got to ensure that when you're training your system and testing the system, the data sets are kept independent. Okay, when you're doing it, the one approach is that in the 80-20 split, it's possible that you could do something like an M-fold cross-validation. Let's, for example, we take a 5-fold as an example. 5-fold means your 100 signals, the example we took, would be split into 5 subsets. Okay, and you would use 4 of those for training, and what's left, the remaining 5th subset for testing. That's 80-20 split. But you would be continuing that process. In the second iteration, you would try to get the classification accuracy of the ML by training that with subset 1, 2, 3, and 5, and you would be testing with 4. Okay, and you would do the same thing, that you would train with 1, 2, 4, and 5 and test with 3, and so forth. So by this way, you are kind of introducing variations in understanding whether your ML is holding on, to the extent that you are exposing that machine learning to different testing sets and different training sets, and making sure they're independent to each other. So this is 5-fold. You could go the same thing with the 10-fold cross-validation. And 10-fold means 90% of the data would be used for training, the remaining 10% would be used for testing, and you would repeat this in 10 different ways. Okay, so it's very simple for concept. And once you do that, you would take the average of the classification accuracies you got with the different folds, and that result that you're getting is seen to be much more robust, which kind of gives you a guarantee the outcome of this cross validation would hold on even if you scale up your ML applications. Okay, so that's another way to ensure, in simple terms, the performance of your ML technique in the way of cross-validation. And here we have taken the 5-fold cross-validation. It's been shown through experiments in biomedical application. 5-fold cross-validation is good enough to give robust results. Obviously, you have more the fold, more time it takes. Like a 10-fold, you have to go through this thing 10 times. Some people even do leave one out cross-validation, where one test sample is taken out and you train the system with the remaining n-1 samples. Okay, and then you can imagine this goes through n times, and it's very, very time consuming. That's called a leave one out, leave one sample out, or we leave one subject out type approach. Okay, it's not anymore 80-20 split or 90-10 split that we have been talking about. Okay, so the various forms to do cross validation, and it again depends on how much time you have in your hand. An optimal way would be a 5-fold cross validation. Okay, then final aspect is something called ROC, Receiver Operating Characteristics Curve. This receiver operating characteristics is something very specific to the medical community. If you were to talk to any physicians or people in the healthcare domain, it's very difficult for them to understand the things we discussed so far. Things like cross-validation, training, testing, and things like that. They tend to ask the results to be reported in the form of ROC. They understand this ROC curve very well, and it's an accepted practice. That now, what is this ROC? It's nothing but plotting what you had before. Okay, so you would take in the x-axis a plot of 1 minus specificity in the x-axis, 1 minus specificity, And on the y-axis, you would take the sensitivity. Okay, in other words, the true positive rate, sensitivity on the y-axis, 1 minus specificity on the x-axis. If you see that 1 minus specificity is also called the false positive rate, okay, you would take that. And with this one, you would plot for different cutoff of the classifier, you would plot this ROC. And when you plot this one, the ROC will look like a rectangle. Okay, so many cases, for example, if I'm plotting for different points, I might get something like that. So this ROC is kind of a plot within the rectangle. Now, within this ROC, this curve, we have something called the area under the curve. Okay, so this area under the curve is nothing but this shaded portion. So what is the area occupied by that is a metric that the medical community appreciates it. Okay, so if you take an ideal case would be something, an area would be like this. This is an ideal case where there is 0 false positive rate and 100% true positive rate. And this curve would look like a rectangle. Okay, so that particular rectangular curve, which this aspect of it, if I get the area under this rectangular curve, it would be the entire rectangle, and you could see this area is 1. Okay, so 1 or 100% is the best area under the curve value. They call it AZ. Okay, AZ, area under the curve. So if you tell the medical community that the area under the curve was 100%, it means it's a perfect machine learning classifier, and the confidence level of the doctors would be very high in relying on your results. Okay. On the other hand, with the blue curve which we had, definitely this area under the curve of the blue curve is not 100% because it's just taking a part of the this area under the curve plot. And maybe, for example, here I could say this area under the curve is around 65%. Okay. Okay. So when you tell again to the medical community this area under the curve 65%, they will get the idea that the ML technique that you have developed is obviously having some false positive rate, and that needs to be corrected. In other words, the results are not always reliable. The confidence interval with the outcome that you got is only 65%. Okay, so that's what you would do. I mean, as you could see, this value is again dependent on the confusion matrix values. We didn't get it just out of blue. We know what sensitivity and specificity from the confusion matrix that we just discussed, A, B, C, D values. Using those values, when I plot as a graph, this graph, and I use the area under the curve AZ, and if the AZ value, which is normalized from 0 to 1, 0 to 100%, if that value is, for example, 0.65, like what we got, which is nothing but 65%, then you would say there is some level of confidence, but not fully they're thorough with the decision that's been made. So higher the AZ, better the performance. And that's another way to indicate how good is your ML performance. So to summarize it, in terms of the ML metrics, we just talked about the area under the ROC curve or AZ. We talked about classification accuracy. That's another way, and that's typically in non-medical application, people just go by the word classification accuracy, then which also has the thing inbuilt, sensitivity and specificity, specificity. So these are kind of the 4 interrelated performance metrics of an ML technique. Okay, ML technique. Okay, so these are objective ways of telling how good your ML design was. Okay, and you would try to report these things whenever possible. And this again is dependent on your machine learning model, which is dependent on the data set that's been collected. Okay, so these metrics might change with a different volume or numbers in the data set. Okay, and that's something that needs to be kept in mind. Okay, so if you come across work which has done, for example, arrhythmia detection using ECG, they would have applied on a small data set, maybe coming from a small location, and they would have reported 100%. We cannot take that result and tell, okay, arrhythmia detection is 100% accurate with this methodology, because the moment you test it with a larger, a bigger data set from a different location, you will see the results are changing. Okay, so it all comes to the point, it's all interrelated, like your data set, how diversified they are, how good is your pre-processing, how good is your ML technique, and how you're trying to report that in a way that people appreciate and understand in a more standardized way. They all are interrelated. Okay. Thank you.